My name is Jack. We're going to be talking all things energy. So first and foremost, I want to ask, what all do you think of when I say energy? What does energy make you think of? Yes? What was that? Doing a what? Moving a lot? Perfect, yeah. All of that movement. Lots of energy. I'm moving around a lot. I got a lot of energy. That is definitely a very important part of energy. What else? What other things do we think of? Do we think of anything else? Yes. Right here. Energy what? Energy drinks? Those are good too. That's how you get all the extra energy that makes us move around a bunch. Over here. What does energy make you think of? Power? Ooh, that's a good one. That's a very scientific term. Power. I like it. Right here.
The sun.
The sun. Very good. Another great source of energy for us. We'll do one more. Running, yes. Another thing that we do to get out some of that built up energy we have from our energy drinks. So energy is lots of things. We all have energy. We use energy every day. But energy in science, there is a more broad definition that we like to use, which is that energy is the ability to do work. And that is a very kind of abstract way of saying it, but essentially what that means is the ability to do work is the ability to cause change in motion. So if we are able to cause a change in motion, cause a change in an object, that is energy. So energy is the ability to do work. Now lots of things have energy, and I have up here my trusty basketball to do our first couple demonstrations. So I'm gonna hold this basketball out straight in the air, right next to me, and who can tell me, does this basketball currently have energy? What do you think? Raise your hand if you think, yes it does. Ooh, some of us think so. Raise your hand if you say, no way, that basketball is staying still. Raise both hands if you say, I have no idea. I'm not quite sure. It's all right too. We're gonna learn. So, if I were to let go of this basketball, who can tell me what would happen? In the front. Yeah. It would have energy. What would it do? Bounce. It would fall and it would bounce. Very good. So we know that while it's falling it has energy, but it turns out, since it wants to fall, it has a very special type of energy. I heard some of us might be saying it. Do we know what it's called? Potential energy, yes. It has potential energy, which is a form of stored energy. So since that ball wants to fall all the way to the ground, and I'm holding it up, it has stored energy. And then once I let go, all that energy is released, and it allows that ball to fall down. So, things can have stored energy from things like gravity. Gravity can pull on a ball and give it stored energy so that when I let go, it falls all the way to the ground. So we know that while it's stationary, it has stored energy. What about while it's falling? What do we think? Does it have energy while it's falling? Over here. What was that? Yes, it has a different type of energy. It has our other main type of energy called kinetic energy. So potential energy is stored. When I let go, it falls and has kinetic energy. So kinetic energy is the energy of motion. All things that move have kinetic energy, whether it is falling and bouncing, or rolling across the stage, or any other type of motion. Even me walking around, I have kinetic energy while I move. So any type of motion is kinetic energy. And we can transfer energy between the two. So while it's stationary, it has all that stored potential energy, and all that potential energy becomes the kinetic energy of it falling. So we can transfer between those two energies. Now I want to take note, when I drop it, is it bouncing up as high as I dropped it? Is it? No. So what's happening here? Because as a famous scientist once said, my friend Einstein, energy cannot be created and it cannot be destroyed. So there's no energy that's being created, no energy being destroyed, but we know it's not bouncing to the same height, so some of that energy is going somewhere. And it's our job to figure out where it's going. Can anyone tell me what is happening to that energy? Do we have any guesses? One guess, yeah. It's using the energy to bounce, yes. So one of that part of that bounce is that we can hear it. So some of that energy is transforming into sound energy. So us being able to hear it is taking away some of that energy. It's also being transformed into light. We don't even notice it. It's a light wavelength that we can't really see. It's a very small amount, but some of that energy is being turned into light. So it's being turned into light, it's being turned into sound, it's also being turned into thermal energy, warming up this basketball just a little bit, not really enough to notice, but it is there. And so all of those transformations of energy take away some of its energy, and so it can't bounce up as high as I drop it. Very interesting. All right. Well, we know energy can be transformed between kinetic and potential. We also know that energy can't be created or destroyed, and that it can be transformed between types of energy. I also have this tennis ball up here. I'm going to do the same drop test. We notice that it doesn't quite bounce up, it bounces at the same height to my hip. But I'm curious, if I were to drop these two together, what might happen? Do you have any guesses? Ready?
I did this experiment in school.
Oh, we think the top ball might go higher. Do we have any other predictions? Any other guesses? All right, you think that they're gonna bounce. Okay, I need a volunteer to help me with this one to make sure that we can get this drop test done well. My friend here, thank you for answering the question. If you wanna come up, your job is going to be to drop the tennis, or the basketball. I'm gonna drop the tennis ball and we're gonna see what happens when they land. Does that sound good? All right, if you wanna come over to the center stage with me, right, perfect. Facing up, what's your name, my friend? Noah? Everyone say hello to my friend Noah. I know. Thank you for helping me, all right. So you're gonna hold out the basketball, you're gonna stand center stage right here and face out towards the audience. You're gonna hold that basketball right in front of you like this. I'm gonna hold this tennis ball on top. We're gonna find out what happens. Just as a warning to our audience, be aware, I'm not quite sure what's gonna end up, so keep your head on a swivel. All right, we ready? In 3, 2, 1. Oh, heads up. Good catch, thank you. All right. So we saw that that tennis ball bounced super high, bounced much higher than it does when I drop it on its own. So what's happening to that energy? Why is it bouncing so much higher? What's happening there? Right here. You have a guess. What's happening with the energy? Oh, I gotcha. Sorry. Any guesses about where that energy, what's happening with the energy? Very interesting, yes. So, that tennis ball has taken the energy from the basketball. That basketball shared its energy with the tennis ball, and that allowed that tennis ball to launch even higher than it can when it bounces on its own. So I want to do this experiment one more time. I need another volunteer to help me do my drop test. Right there, thank you for helping answer. If you want to come up, we're going to do the same exact experiment. We watched the tennis ball last time. We saw that it bounced really high, so I want to pay attention to this basketball and see what happens to the basketball while it bounces. So, center stage, arms straight out. All right, and we're gonna drop it. We're gonna say 3, 2, 1, and then drop it. So keep your eye on the basketball. Unless this happens to be coming towards you, then feel free to watch this. 3, 2, 1. Heads up. Perfect, thank you so much. All right, so did we notice what happened with the basketball? Did it bounce as high as it does on its own? It bounced just a little bit. And that is because the energy was being shared with the tennis ball. And since it sent all of its energy away with this tennis ball launching it across the room, it didn't have as much energy for itself to bounce up. So we know energy can't be created or destroyed. No matter what we do, the energy is being shared between things. So by launching this really high, my basketball used up some of its energy and wasn't able to bounce as high. So we have different types of energy. We said the two main types, kinetic and potential. And those can come in lots of different forms. One of those forms was gravity, holding things up and letting them fall. But another form of potential is elastic. So I have my major massive rubber band up here. It is super, super stretchy. And by stretching it out, I am storing energy. I am creating potential energy. But in this case, instead of letting gravity fall, it is that elastic stretchiness. So it is elastic potential energy. And so we can transfer energy we can change its form from potential to kinetic. So if I pull back my rubber band just a little bit, I give it some stored energy, some elastic potential, and when I let go, all that potential energy becomes kinetic energy. And I can launch things all sorts of ways. But if I were to increase the amount of potential energy in my rubber band, I can change more energy into kinetic. And so we can launch this rubber band even further. So I need a volunteer to help me. We're going to stretch out this rubber band really, really far, try and give it a lot of potential energy, and then we're going to see how much kinetic energy, how fast we can launch it away. I am going to take it right in the front here. Thank you so much. What is your name, my friend? Juliana. Everyone say hi, Juliana.
Hi, Juliana.
Hi, Juliana. Thank you for helping me. So your job is going to be to hold this end of the rubber band. I'm going to hold this side. We're going to stretch it out as far as we can. We're going to do 3, 2, 1, and then you're going to let go, and we're going to watch it across the room. Does that sound good? All right. So we're going to try and stretch it out, give it a lot of potential energy. And then 3, 2, 1. Woo! I'm so sorry. We'll do it. You want to try one more time? All right. In 3, 2, 1. There it goes. All the way to the rocket. Very nice. Thank you so much for helping me. Round of applause for my friend Juliana. Thank you so much. So we can see that by increasing the amount of potential energy that we give an object, we can get more kinetic energy back out of that object. So by increasing how far I stretch it, I increase that stored energy, and then I can launch it faster and further, getting more kinetic energy out. So we have gravitational potential, elastic potential. Another type of energy that we have that we use on a day-to-day is thermal. Thermal energy is the energy that we feel as heat or cold. And that energy is actually the energy of molecules, the motion of the molecules in an object. The faster those molecules move, when they're going really, really, really fast, we feel that as heat. So things that feel hot have molecules moving super, 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 super fast. But on the other side of that, when we feel cold, it is because those molecules are moving really, really slow. So I brought with me something very special called liquid nitrogen. And liquid nitrogen is a very, very, very cold liquid. So cold, it is colder than the ice we put in our drinks. There we go. So it is super, super, super cold. And with it, we can make different molecules move very, very, very slow. So I'm going to pour out some in my bowl up here, and we will see what it's like if we are to slow down the molecules of an object and make it very, very cold. There we go. All right. So I have my bowl full of liquid nitrogen. You might see some of that fog coming off. That is actually fog. That is what is the water in the air getting so cold it is turning into fog and rolling away. So all of that is just water turning into fog straight out of our air. And I realized we're going to use this one over here. Forgot, I tossed it to the side. I have my balloon. It's a little bit small, but we know that balloons are nice and stretchy. They like to float. But I'm going to put my balloon in my liquid nitrogen, and we're going to see what happens to the molecules of my balloon when it gets really, really cold. So the liquid nitrogen is cooling down that balloon and causing those molecules to go from really, really fast to very, very slow. And it can kind of change how objects react to things. So you can see that what is normally very elastic and stretchy balloon is becoming very crisp and crinkly. And the air inside is actually flattened down. It has gone so slow that it has flattened out my balloon. Oh, when we pop it. Very unfortunate. So usually, this balloon was a little bit old. But the molecules in that air were slowing down. It caused that balloon to collapse. And if I had a fresh balloon, those molecules, as they were able to heat back up in the air, they would be moving faster, and the balloon would return to its usual state, which we were starting to see until the elasticity of my balloon gave out. So, we can change object's temperature, the thermal energy, by making those molecules move really fast, heating it up, or in this case, making them slow down and become very cold. And that can change the properties. A nice elastic balloon becomes really crispy, and the air inside becomes really condensed, really, really small. And with the rest of my liquid nitrogen, I'm going to dump it out, and we're going to get a nice little fog. That fog is safe if it comes to you. You're welcome to feel it. Please do not get up to touch it, but it is, again, just that water vapor in the air around us. So thermal energy is the energy of molecules in objects. But we do have one final form of energy I want to talk about today. And that is chemical energy. And chemical energy is very important as a source of energy that we use every day. We have two main sources. We have renewable energies and non-renewables. Does anyone know what the difference is between them? What is the difference between a renewable and non-renewable energy? Absolutely, yes. So, those non-renewable energies are things like fossil fuels, coal, oil, gas, things that we burn up to use to get energy out of those systems. Those are ones that we cannot really replenish on our own in a human lifetime. Those take long stretches of time to develop, and we cannot make them in our lifetime. So they are non-renewable. Because once we use them, they're all gone. But on the other side, we have renewable energies, things like solar, wind, hydro, geothermal energy out of the ground. Those are things that can be replenished in the human lifetime, and we can continue to use throughout. We can continue to produce or collect that energy at any time. Now, non-renewable energies all rely on the chemical energy in the bonds of those molecules. So, in coal, there's chemical energy held up in the bonds of that coal, and once we light it on fire, we get it really hot, we give it a spark, we light it on fire, it releases all the energy in the form of combustion, fire, explosions. So, I think we should try to see some chemical energy and make some explosions. My first explosion is going to be a massive one. In 3, 2, 1. 3, 2, 1. Oh my goodness. 3, 2, 1. There it is. And we can see that when I first light that match, you see a really big flame at first, and that is all of the phosphorus at the end of my match first igniting and causing a really big explosion, which is the rapid release of energy. So since it becomes that really big flame at first, all of that energy is being released rapidly, and it is considered an explosion. But I think we can do a little bit better explosion than just my little flame right here. So I brought with me some other gases that all have lots of chemical energy stored up in them. And with them, we are able to make much larger and much more interesting explosions. So I'm going to grab out real quick my little blast shields here to make sure we are all staying safe, because that is always the most important thing. All right. So, first and foremost, I have this balloon I brought with me. And this balloon is filled with a special gas called methane. Methane is a gas that has a lot of chemical potential energy. It has a lot of energy in those bonds. So when you add some kind of flame, some kind of spark, all of those bonds rapidly release their energy, and we get an explosion. So I'm going to put on my protective gear, my face shield. And so we know that energy cannot be created or destroyed. So when I release the energy out of this balloon, it is our job to figure out where the energy goes. So when I bring over my torch, I'm going to ignite my balloon with a flame, and you all need to pay attention and see if you can find out where that chemical energy, the energy in those bonds of the gas, are going, what is happening to them. Does that sound good? This is where things might start getting loud. These first few balloons aren't too loud, but if you are a little bit sensitive to those types of things, we can always cover our ears. So if we want to cover our ears, this is the time to do so. There are a couple later on that we will all have to cover our ears. But for now, it is only as you see fit. All right. So I'm going to light it, and we want to see where all that energy, that chemical energy, is going in my balloon. Balloon in 3, 2, 1. Very nice, much better explosion than our last time. All right. So who can tell me, where did all that energy go? What happened to the energy, that chemical energy in my balloon? My friend right there, Cleveland shirt. What's that? It came out of the balloon, yes. Can you tell me, how did it come out of the balloon? In what ways? What types of energy came out of the balloon? Yes, it like collapsed, it was really rapid. Were we able to hear that balloon pop?
Yeah.
Yeah, so some of that was sound energy. Were we able to see that big fireball? I think so. So some of that energy was turned into sound when our balloon popped. Some of it was turned into light in that big fireball. And some of us might have even been able to feel it in our chest a little bit, and that will have been kinetic energy of the air around us, actually. So I have another balloon. This one is also filled with methane gas. So it's the same as our last balloon, but I added another chemical, a slightly different chemical, to it called strontium chloride. And so we can actually change how those chemical reactions occur if we add different chemicals into the mix. So, the last one we saw, that big, nice fireball, this one, we're going to see something similar, but I want you to focus and see if you notice anything different that strontium chloride is changing. So look close at that nice big fireball and see if we notice any differences between the last one and this one with our strontium chloride. Same as last time, feel free to cover your ears. This one should not be too loud, so it is not required if you do not feel that it is necessary. All right, I'm going to turn on my torch and balloon in 3, 2, 1. All right, do we happen to notice anything different about that fireball? Might have been a little hard to tell right there in blue. What was that? Ooh, sorry. It was longer. That it might have been a little bit longer. Yeah? Yes. We might have also noticed a slight difference in the color. So strontium chloride actually burns usually a very bright red. Sometimes depending on the amount, the mixture, it might be a little bit more orange. Strontium chloride is actually what we put in those road flares to make them nice bright red when you see those by the roadside in the case of emergency. So that strontium chloride is changed our fireball to be a nice bright red, a nice orangey red. They are also used in things like fireworks. Anytime we want to change the color of some kind of combustion, of a fire, to be something a little bit different, strontium chloride we can use to make it more red. This one is also methane gas, so it should burn similarly, but I have a separate chemical called copper chloride. So this one is going to change the color of our fire as well, but it might be a different color, so we're going to have to watch close attention to see if we notice what color it is. A little hint, our Statue of Liberty is made out of copper. All right, fire and balloon in 3, 2, 1. So we might have noticed that fireball was nice and green, and that was due to that copper chloride changing the reaction of that combustion reaction to have a nice green color. That again is used in things like fireworks and different things like that if we ever want to make a nice bright green reaction with our chemicals. So those three were methane gas. Methane is very reactive. It burns pretty bright, but it burns kind of slow. It takes its time, so we get a nice fireball that hangs in the air. With these other two balloons, I have a different gas. This one here is hydrogen. And now hydrogen has a lot more energy in its bonds. In those bonds, that chemical energy, it has lots more built up. And so hydrogen reacts a lot more intensely than our methane does on its own. So this is the point where we are going to need to start covering our ears. So when I go grab that torch, before we're able to pop it, I need to make sure we all have our ears covered, because our hydrogen is very reactive. It has lots and lots of chemical energy stored up. And so It is going to release that energy as we've seen before, but much more fast, much more intense. So it's going to burn louder, brighter, and faster. Let me grab out. I do need to make sure that we are all covering our ears, so I'm going to grab out. I do have some headphones if we are covering the ears of our little ones and need to protect our own hearing. Let me grab out. Here is one set of headphones. All right, are we all good? Are we all able to cover our ears otherwise? Make sure we're all good? Okay. I think we should be okay. Now that our friends are able to cover their ears, protect their hearing. And I guess importantly, I should do the same. I'm going to put on my headphones as well. Because one of our priorities here at the Science Center is always making sure we are doing science safely. It is one of our biggest priorities, always very, very important to us. All right, so before I light this torch, I want to make sure we all have our ears covered. We are all protecting our hearing. Make sure we all have our ears covered. Perfect. Going to light. And balloon in 3, 2, 1. So we saw that that energy burned much faster, much brighter, and released a lot quicker, so that fireball did not hang in the air quite as long as those methane fireballs did. So that is hydrogen on its own, but an important part of any chemical reaction, any combustion reaction I should say, is oxygen. Oxygen is important for any type of chemical reaction that has to do with combustion or flames. And so in this balloon here, I have not only hydrogen, but I've added some oxygen in this one as well. And that oxygen is going to act as a catalyst, and we will see how introducing oxygen into that balloon will change our reaction. But a little hint, it will accelerate it. It's going to act as a catalyst, making that reaction that was already faster and brighter than our previous ones, even faster, even brighter, and also even louder. So we do need to be covering our ears one more time for our final balloon of the show. We have our hydrogen, oxygen mixed balloon, ready to go. We all look great with our ears covered. Perfect. All right. Torch on and balloon in 3, 2, 1.
Oh my god. That one was actually
So
loud.
we've seen that oxygen made that reaction much faster. It acted as our catalyst to make a much more intense reaction. It's important for any combustion reaction. And with that, I am out of balloons. We are at the end of our show. We have talked about all sorts of energy, kinetic, potential, different forms of energy, gravitational, elastic, chemical, thermal,